Good afternoon, everyone. So today I will be presenting a part of my PhD thesis work titled "Reaction Textures in Ultramafic Rocks: Evidence for Supra to Sub-solidus Reaction Continuum." So now we all of us have seen reaction textures in our time of a study whenever we have looked at rocks. So reaction textures are what? Basically, they are simple textures that have formed from a pre-existing mineral due to some kind of reaction, either reacting with another mineral or a breakdown reaction or any kind of that. Now, coronas and symplectites are some of the most common reaction textures that we find in igneous and metamorphic rocks, right? So, coronas can be defined simply as concentric textures in which we have a mineral at the core surrounded by multiple concentric layers around it. And they are mostly radial in nature. And symplectites, when we say about symplectites, we generally mean that it is an intergrowth of two or more minerals in which generally at least one of the mineral are show that vermicular habit or that worm-like habit. Now, if we look at the corona textures, one of the most common corona textures that we find is that at the contact of olivine and plagioclase, which is very common in mafic and ultramafic rocks. Now, some authors have said that these textures have formed through igneous processes and involve some melt phase. Others have said that no, it has formed through a sub-solidus solid state metamorphic process. Autometasomatism is sometimes also given as a possible mechanism for formation of such coronas, right? Similar to this, even symplectites are sometimes attributed to a solid state process and sometimes to a supra-solidus process in which there is involvement of a late stage interstitial melt. So now there exists a debate whether these coronals and symplectites such textures are of igneous origin or of metamorphic origin. Now, to answer this, we look at some ultramafic rocks from the eastern part of India. Now, the current ultramafic rock has been taken from the Chotanagpur granite gneissic complex, which is a geological terrain located in the eastern part of the India. It is a polydeform, polymetamorphosed proterozoic terrain that is essentially related to the important because the study is important because of its role in the amalgamation of India during the north-south amalgamation of India. Now, the currently studied ultramafic rocks, if you see in this, sorry, let me bring my pointer out. So, if you can see here we can see that there is a shear zone called the North Pilia shear zone. Now, along this shear zone, multiple collisional granites have been reported, and the currently studied ultramafic rocks basically occur as enclaves within one of such porphyritic granite bodies, right? So this is the field appearance of the studied ultramafic rock. It occurs as enclaves we surrounded by the porphyritic grains. You can see in field the presence of some large pyroxene grains and some feldspar grains. Now look at the contact of this porphyritic granite and the ultramafic body. You can see that it is very sharp. It is very sharp. It is slightly curvilinear. Notice that there is no quenching texture along the contacts. The contacts are very sharp. We do not see any kind of quenching textures like what that we expect. So this possibly indicates that at the time of the contact happening between these two magmas or these two rocks, they were both at very high temperatures. Now, if we look at these two images, we can see this sharp curvilinear contacts again. We can see possibly indicating of that both have some different viscosities due to this curvilinear feature, we can say. Similarly, if you look at this fabric, we can see that it is more closely oriented as we go near the mafic body, but as we go away from it, it generally tends to not be that strongly oriented. So there appears to have been also some kind of flow or some kind of ductility in these rocks during their emplacement, right? So now if we look at the thin section of these rocks, we can find the main minerals are olivine, orthopyroxene, clinopyroxene, plagioclase, biotite, amphibole, spinel, and apatite. Of these, olivine, orthopyroxene, clinopyroxene, and plagioclase, and spinel and apatite are generally primary, but orthopyroxene and the biotite and amphibole are secondary, whereas we also find secondary clinopyroxene, biotite, and amphibole. These are the accessory minerals. So broadly, we can divide these ultramafic rocks into two types. One of some thin sections contain olivine and the others do not. So here is an example of a thin section that contains olivine. You can see these grains. And here is an example of a thin section that does not contain olivine. Now, olivine generally occurs, almost always occurs enclosed within orthopyroxene grains. Here you can see a big multiple olivine grains generally engulfed by enclosed within orthopyroxene grain that is of a single interference color, possibly indicating the interconnected network of fluids or melts, which basically reacted with pre-existing olivine typical peritectic reaction to form this orthopyroxene network along the olivine grains. Now, other than this, orthopyroxene also occurs as rings along olivine. So there also we can find two different types of rings. If you look at this particular ring, better in CPL, you can see that these are very layers of very uniform thickness that generally do not show a very invading boundary towards the olivine grain, and they generally tend to mimic the boundary of the enclosing olivine grain. Whereas the other ones, they generally do not. They generally have this ununiform thickness. They generally show this invading contact or this curvilinear contact. So possibly this mimicking OPX layer is basically a sub-solidus process that formed due to diffusion control processes, whereas these ununiform or non-mimicking layers are possibly the result of the typical olivine plus melt reaction forming my peritectic OPX, right? Now, if you look at this picture also, you can see that around this olivine, we have some orthopyroxene layers, which generally follows this mimicking nature is present here also. Now, if you notice one thing, you'll see that these mimicking layers or these orthopyroxene layers that mimic the grain boundary or the internal olivine grain, they form no matter whatever the contact of the olivine grain was initially. So like here is clinopyroxene, it is still forming. Here it is plagioclase, here is that is still forming. But in case of the previous picture where we saw that the this kind of non-uniform or possibly melt-derived orthopyroxene coronal layers, they are only found along contact between olivine and plagioclase, right? So also at some places we do find that the original olivine plagioclase contact has been preserved. So based on this, we can say that there are basically two types of OPX corona in this talk. We have one supra-solidus OPX corona, which generally do not mimic the enclosing olivine grain. They show resolved olivine OPX contacts and non-uniform thickness, and they only form at olivine plagioclase grain boundaries. Whereas the sub-solidus orthopyroxene rings, they form no matter whatever the contact is. So they are possibly breakdown reactions where olivine is breaking down to OPX. Now, they generally show a smooth context and uniform thickness. Now, it is interesting to note that the composition of either of these two layers generally do not show any variation, right? Now, if you, other than that, OPX also occurs, if is visible here, as granular aggregates. You can see that these granular aggregates of OPX are showing a very sharp boundary with the adjacent plagioclase boundaries, almost like abating at those boundaries. We conclude that these are possibly result of formation from late stage interstitial melts, where the plagioclase has possibly already formed. That's why it has the melt has basically crystallized following the grain boundary of the the already crystallized plagioclase grains. Here you can see the same in CPL. Now, other than that, OPX is also found as big grains, typical euhedral OPX grains. Now, coming to CPX, CPX occur both as such big grains like this, typical euhedral primary igneous grains, and also as CPX and plus symplectites. You can see that these CPX and plus symplectites always form along the boundaries of plagioclase slabs. More greatly visible in this picture, you can see that along a supposedly triple junction type or along the grain boundaries of three plagioclase slabs, these CPX plus pledge symplectites have formed. These are generally attributed to the formation of through late stage interstitial fluid. So some fluid possibly was here that reacted with the pledge and formed this particular CPX symplectite. Now, other than that, CPX symplectites are also found to form from orthopyroxene grains, like the primary orthopyroxene grains. They also break down to form CPS symplectites like this, that is CPX and plagioclase symplectites. Here you can see that the orthopyroxene is breaking down into CPX symplectites. You can see in the CPL very nicely that the interference color has changed along the boundaries and resembling that of CPX. The chemical composition also shows the same. Now, if we go to the other type of OPX layers that we found, that is OPX coronas, there also we can see that the OPX coronas are also at places breaking down into CPX symplectites. So basically, you can see that here we have olivine, here we have that orthopyroxene layer, that is coronal layer, that is breaking down into CPX plus symplectites. Now, so another thing, we sometimes find CPX symplectites that is surrounded by CPX grains. There is no OPX. So apparently that might contradict our previous observations that some clinopyroxene symplectites are forming from OPX also, because there is no OPX here. But once we do X-ray mapping of this area, so this is the symplectite that you are seeing in this image. So this is my symplectite that I'm looking at. So if you look at it, these bright color minerals, these vermicular minerals are my CPX clinopyroxene and hosted within plagioclase. Now, if we look at the MGFE diagrams, we can see that there are some OPX here. Moreover, if you look at this particular X-ray map of MG, you can see that within this CPX symplectites, there is remnant of a OPX grain. You can see here, right? So that means this possibly conclusively proves that CPX symplectites are forming from OPX also, not just from interstitial melts. So if we combine all these observations, we can say that there are two types of CPX plus pledge symplectites. One kind is of supra-solidus, which is forming along olivine plagioclase slabs and abetting along plagioclase slabs. And the sub-solidus kinds are generally surrounding OPX. They generally sometimes contain inclusions of OPX, and they only form at OPX and pledge contacts. Now, the interesting thing is that both these type of clinopyroxene symplectites have this very well constrained composition. That is, their XMG and both their XCA, they are very well constant. They do not show any variation. Now, other than that, in this rock, we also see that there are big plagioclase grains, not less, that sometimes show zoning, and the core is generally more anorthitic rich in that case. Now, after all these symplectite sub-solidus reactions and the OPX sub-solidus reactions has taken place, the rock is mostly replaced by biotite first. So here you can see the inclusion of CPX symplectites within big biotite grains and OPX, which have replaced. So the biotite is my later phase here, replacing the earlier minerals. Here you can see the inclusion. Here you can see the replacement of biotite by clinopyroxene symplectites by biotite. And finally, we have an amphibolitization in the rock where amphibole is replacing biotite or any other mineral. So here you can see amphibole plus spinel layers are forming, that is typical of corona texture. That is typical in metamorphic rocks that we are seeing, right? So compositionally, there is no difference between the OPX of any variety, neither of CPX, but plagioclase shows some variety, that is the granular aggregates that we have within that plagioclase sometimes show higher amount of XNA, right? Otherwise, we generally do not see any varieties. So this is the general situation that we are suggesting, that the rock has taken place. So olivine is one of the earliest forming crystals, followed by OPX, CPX, peridactic OPX, those big interconnected grains, followed by the OPX coronas, followed by the CPX symplectites from melts, then granular OPX, plagioclase forming along the way, Then in sub-solidus, we have olivine to OPX breakdown, then OPX and pledge reacting to CPX pledge, finally biotinization and yeah, your amphibolization. Now we have done some reaction modeling. It shows around 3 to 6% of volume increase due to the CPX plus pledge symplectite reaction formation. Now pseudosection modeling we have done. So these are the parameters that we have taken in the bulk. So we can find the CPX plus pledge pseudosection or the field here. We plot the isoplees of both the CPX and pledge. We also plot the volume isoplees and we come to a pressure temperature of around 925 degree and 7.2 kilobar. This is followed by the modeling for the hydra system amphibole bearing. This is the pseudosection that we get. Now olivine and garnet is also present in addition to amphibolous spinel, but since their volume is very low, less than 1 or 2-3%, so we have not chosen that, and we have used this 2% of H2O to construct the diagram. But the composition isoplees for spinel does not match, so we do not consider this as a well constant pseudosection because the pressure temperature is not that well constant from here. So finalizing the PT from geothermobarometry and pseudosection, we can see that the anhydrous reaction is taking place at a very high temperature of 925 and 7.2 kilobar. And the amphibole plus spinel is possibly taking somewhere between 650 or 680 to 750 and around 5 kilobar we think.